All right. Last time we looked at creating global variables, and the way to do that was essentially just to, let's open up eval here. We have this hash table that stores all globals. Right now, it defaults to a size of 10, but hash tables can grow dynamically. One thing that I found interesting while implementing this is I was under the impression that OCaml was like a purely functional language and didn't have immutable data structures, or didn't have mutable data structures, I should say. But hash table is a mutable data structure. So when we evaluate a declaration, in other words, var something is equal to something, we add that something to the hash table, the global's hash table. And then when we evaluate the expression, if it's an identifier, we look for it in the globals table and then return it back. Right now, I'm not doing a whole lot of error checking and things like that. So I'll do that in another live stream. There's quite a few error checks that I have to go back and do. Right now, I'm not even handling parsing errors or anything like that. So I got a bit of work to do on that. All right, so let's go ahead and continue on with assignment. It's possible to create a language that has variables but does not let you reassign or mutate them. Haskell's one example. It's interesting that they use the word mutate. Mutation is not the same as reassignment. Mutation is when you have a data structure that its place in memory actually changes. Assignment is when you have a reference to a place in memory and you cannot reassign that variable. So a little bit of a semantic issue there. SML supports only mutable references and arrays. Variables cannot be reassigned. Rust steers you away from mutation by requiring a mute modifier to enable assignment. Mutating a variable is a side effect, and as the name suggests, some language folks think side effects are dirty or inelegant. Code should be pure math that produces variables, crystalline, unchanging ones like an act of divine creation, not some grubby automaton that beats blobs of data into shape one imperative grunt at a time. I find it delightful that the same group of people who pride themselves on dispassionate logic are also the ones who can't resist emotionally loaded terms for their work. Pure side effect, lazy, persistent, first class, higher order. So we got some digs at FP going on here. The guy who created Crafting Interpreter's book actually wrote his own language. I think it's called Ren. That is better Lua in a sense, but it's more object-oriented, so there's clearly a preference that he has. LOX is not so austere. LOX is an imperative language, and mutation comes with the territory. Adding support for assignment doesn't require much work. Global variables already support redefinition, so most of the machinery is there now. Mainly, we're missing explicit assignment notation. Okay. That little equal syntax is more complex than it might seem. Like most C-derived languages, assignment is an expression and not a statement. As in C, it is the lowest precedence expression form. That means the rule slots between expression and equality identifier equals assignment. This says an assignment is either an identifier followed by an equals and an expression for the value, or an equality, and thus any other expression. Later, assignment will get more complex when we add property setters on objects like instance.field is equal to value. All right, so now an expression is either an assignment or an equality. That doesn't quite jive with what we've got so far. Let's open up the evaluator in the parser. Right now, an expression can be one of all these things, so I'm not entirely sure what's going on here. Assignment, expression, assignment, identifier equals assignment or equality. Let's continue on and see what it does. It has taken a token for the variable being assigned to and an expression for the new value. After you run the AST generator to get the new expression assign class, swap out the body of the parser's existing expression method to match the updated rule. Return assignment. This is where it gets tricky. A single token look ahead recursive descent parser can't see far enough to tell if it's parsing an assignment until after it has gone through the left-hand side and stumbled onto the equals. You might wonder why it even needs to. After all, we don't know we're parsing a plus expression until after we finish parsing the left operand. The difference is that the left-hand side of an assignment isn't an expression that evaluates to a value. It's sort of a pseudo-expression that evaluates to a thing you can assign to. On the second line, we don't evaluate a, which would return a string before. We figure out what the variable a refers to, so we know where to store the right-hand side's expression value. The classic terms for these two constructs are I value and R value, or L value and R value. All the expressions that we've seen so far that produce R values are R values. An L value evaluates to a storage location that you can assign into. We want the syntax tree to reflect that an L value isn't evaluated like a normal expression. That's why the expression assign token has a token for the left-hand side, not an expression. The problem is the parser doesn't know it's parsing an L value until it hits equals. In a complex L value, that may occur many tokens later. So make list.head.next equals node. We have only a single token of look ahead, so what do? We use a little trick and it looks like this. If match equals token equals previous expression assignment, if expression instance of expression variable token name equals expression.variable expression.name, return new expression.assign name value. Most cycles for parsing assignment expression look similar to that of the other binary operators like plus. We parse the left-hand side, which can be any expression of higher precedence. If we find an equals, we parse the right-hand side, and then we wrap it all up in an assignment expression tree code. One slight difference from binary operators is we don't loop to build up a sequence of the same operator. Since assignment is right associative, we instead recursively call assignment to parse the right-hand side. The trick is that right before we create the assignment expression node, we look at the left-hand side expression and figure out what kind of assignment target it is. We convert the R value expression node into an L value representation. This conversion works because it turns out that every valid assignment target happens to also be valid syntax as a normal expression. Consider a complex field assignment like this. New point x plus 2, 0, dot y is equal to 3. The left-hand side of the assignment could also work as a valid expression. The first example sets the field, the second gets it. This means we can parse the left-hand side as if it were an expression and then after the fact produce a syntax tree that turns it into an assignment target. If the left-hand side expression isn't a valid assignment target, we fail with a syntax error. That ensures we report an error on code like this, a plus b is equal to c. Right now, the only valid target is a simple variable expression, but we'll add fields later. Okay. The end result of this trick is an assignment expression tree node that knows what it is assigning to and has an expression subtree for the value being assigned, all with only a single token of look ahead and no backtracking. So I've missed a couple side notes here. How far do I need to go? In some other languages like Pascal, Python, Go, assignment is a statement. Okay. In fact, the names come from assignment expressions. L values appear on the left side of the equals in the assignment and R values on the right. Since the receiver of a field assignment can be any expression and expressions can be as long as you want to make them, it may take an unbounded number of tokens of look ahead to find the equals. We report an error if the left-hand side isn't a valid assignment target, but we don't throw it because the parser isn't in a confused state, where we need to go into panic mode and synchronize. You can still use this trick even if there are assignment targets that are not valid expressions. Define a cover grammar, a looser grammar that accepts all the valid expressions and assignment target syntaxes. When in hidden equals, report an error if the left-hand side isn't within the valid assignment target grammar. Conversely, if you don't hit an equals, report an error if the left-hand side isn't a valid expression. So way back in parsing chapter, I said, we represent parenthesized expressions in the syntax tree because we'll need them later. This is why we'll need to be able to distinguish these cases. Okay. All right, assignment semantics. We have a new syntax tree node, so our interpreter gets a new visit method. For obvious reasons, it's similar to variable declaration. It evaluates the right-hand side to get the value, then stores it in the name variable. Instead of using define on an environment, it calls this new method. The key difference between assignment and definition is that assignment is not allowed to create a new variable. In terms of our implementation, that means it's a runtime error if the key doesn't already exist in the environment's variable map. The last thing the visit method does is return the assigned value. That's because assignment is an expression that can be nested inside other expressions like so. Our interpreter can now create, read, and modify variables. It's about as sophisticated as early basics. Global variables are simple, but writing a large program when any two chunks of code can accidentally step on each other's state is no fun. Alright, so then it gets into scope. I don't think we're going to get to scope today, but we're going to try and implement this assignment thing. Now, the one thing that I'm really confused about is right at the beginning, the grammar that is used here. So expression is now just assignment. An assignment is an identifier following an assignment, or equality, and thus any other expression. Any other expression. I don't know what they mean by equality there. I think what we can do here is say that a statement is either, no, an expression is assignment. Well, we have a declaration here, which is a statement. A statement is either this expression or a print statement. So let's say we were to do something like ooh, it's almost like it's reading my mind here. Identifier equals expression, assign ITE, and then we have to add that to the AST under expression. Okay. So I think the issue with this was this on this side isn't just an identifier. It could actually be an expression in the world where this is to prepare us for being able to mutate a field on an object, essentially. So in the future, so right now, identifier would be fine, but in the future, this would have to be an expression that is assignable. But the problem is we don't want the expression to be evaluated first. Actually, sorry, we want the expression to be evaluated first, but more particularly, when we parse this AST, it needs to know what's, so let me go back to the book here. The issue with this is when we're actually doing the parsing here, we don't evaluate A, which returns string before. We figure out what variable A refers to so we know where to store the right-hand side expression's value. Okay, well that's just the oh, okay, here's it. Single look-ahead token recursive descent parser. It can't see far enough to tell that it's parsing an assignment until after it has gone through the left-hand side and stumbled onto the equals. Okay, so we could try just putting identifier here first. See what that does. There is a way in this MLY file, which is using is it men here? Yeah, men here. there is a way to define precedents and things like that, I think. I'm going to, for now, just do an identifier assign and we'll get that working. And then later on we can add the ability to put an expression on the other side. Okay, so now when we evaluate it, if we see an expression that is an assign, identifier and expression, then, oh, interesting. I wonder if that's correct. Let v equals eval expression e in hash table replace globals id with a value and then return the value. That looks right. Okay. Okay. So we got some errors here. Lots of errors. Okay. So on print.ml, oh, okay. That's right. Because now I have to update this with correct assign here. What do we want to even do with this? We just want to print the expression part probably. Yeah, let's just do that. Forget the identifier, print the expression. Print AST. We want to do something like an assign. Yeah, that looks good. Okay. So that should be those two errors going away, hopefully. Okay, we're back to where we started. So now let's open up our test.lox and see if we can do the example one here. Okay, so we're expecting that to do 2, which it does. Now let's see if we can assign a equal to 3 and then just print out a. Okay, that didn't work. What happened there? Good thing we tested that. So that didn't reassign it. And then when we printed A, it printed the old value there. When we evaluate the expression, we evaluate expression and then replace global's ID value. Okay, let's print the AST and see what we're getting then. Let's go to main. And for now, we're going to replace this with print AST and uncomment that. Okay, so we do see an assign A to 3. AST is correct. So something in our evaluator is not correct. What could be going wrong? Hash table replace replaces a current binding of key in table by binding a key to data. If key is unbound table, binding a key to data is added to table. This is functionally equivalent to remove table key followed by add table key. Okay. And then we return back V. That's fine. So when we do the print statement, we evaluate the expression and then print it. And then when we're evaluating an identifier, we find it in the globals. So var a equals 1 equals 3, 5, shouldn't matter. Let's go back to evaluating now. Eval. Okay, so what is happening here? If I were to say var a is equal to 5, that will probably throw an error, right? Nope. Okay, so it's fine with that. So it is recognizing this as an assignment, but the identifier there is not getting overwritten in the hash table. Okay. Let's do at the time of evaluating the assignment, I want to print something out. So I want to find it and print that thing out. So we're going to do this, find globals ID, and then we're going to say print. Okay. Huh. Did it never evaluate that? Let's just replace this with print string here and eval expression. Let's just print. Nope, doesn't like that. Print expression, I think is what I need. Nope, that's not it either. Eval expression and then print. Eval expression print. Still not happy with that. This expression has type units. Oh, okay, this is supposed to just return back an expression. Okay, yeah, that should be fine then. So let's just evaluate it and return it back. Okay, so assignment never gets evaluated correctly. This may be related to not the parsing bit, but the evaluation bit, about the L value and the R value. So let's print the AST out again and kind of think about how this thing will get evaluated. Okay, so we have a var declaration that's getting evaluated correctly. Var declaration is a statement, and then the next statement we have is an expression statement of assign A5. So the AST is correct for that. So the parsing's correct. And then we have the print statement ID A. Assign A5. So why is it that this assign never gets called? Evaluate an expression. Let's open up the parser. The parser is parsing it as an assignment. The AST is being generated correctly. But assignment is not being called correctly. Just out of curiosity, I'm gonna print a before and after that. Okay. Now we're going to eval that. And it prints out 1 twice. Okay. Um, hmm. Why is that assignment not being evaluated? So I think the thing that's confusing to me is I could imagine that it doesn't know its assignment, but it's already in this form. We can see that it's already the correct AST. And then this bit right here is just never getting executed. Oh, you know what's interesting is okay, so we have the var declaration. What's interesting is when we tried doing print a is equal to 5, that worked. Look at that. And it even printed the here. Right? So when we put a print statement, it evaluated the print statement. Evaluated the expression. Oh, okay. I think I see what's going on. So I think what might be happening is no, that can't be true either. Maybe it is. Maybe what's happening is this equal is being evaluated. I think that might be what's happening. So let's do a print string equal. Okay. Okay, so now if we were to do a is equal to 3 and then print a, here's my theory. We're going to see that equal being printed out, and then we're going to see 1 being printed out. It's going to be equal 1. Nope. Okay, I'm wrong about that too. Oh, because this equal is actually a 2 equals, not 1 equal. Yeah. If we go to the lexer, equals, but then in the parser, you can see, equals there, equals expression. This equal is equal. Okay, so I'm wrong about that. It's not calling a binary operator. But I think something along those lines is happening. It's not evaluating the assignment expression correctly. We had the similar issue with the binary operators at one point, where I forgot to evaluate left and right before evaluating the whole thing. What else might I be forgetting to do? We haven't gotten to controls, so we can ignore that. Groupings are done correctly. Uniops are done correctly. Binops are done correctly. Identifier looks like it's done correctly. We can see if maybe the identifier is being called. It sure is. That's what's happening. So what's happening is it sees that it's got an identifier, or why does it see that there's an identifier though? Because ASD looks correct. AST looks fine. Let's go back to print this real quick. Print AST. Okay, so this expression statement of assign A3 doesn't have any identifier in it. But as soon as I try and evaluate it, it says there's an identifier here, and then evaluates it to 1. What's going on there? Let's kind of crawl the tree again. We have 3 statements. We're evaluating, well, actually, we have 3 declarations. The first one's a var declaration. We evaluate it, we're good. Then we have a statement. So a statement is either an expression statement or a print statement. In this case, let's see, the AST. No, that's what I want. I don't want print AST. I want to see what it's printing out. Expression statement or print statement. Oh, okay, it's right there. Expression statement. There we go. So then we have an expression statement. Oh, I conveniently bypassed the expression statement before. That's what's going on. So I should just evaluate the expression statement. I don't know what ignore means. Oh, okay. Yeah, that's fine. Hey, there we go. That's what I wanted to do. All right, let's go back and see if Copilot remembered what it's supposed to do here. Let's. Nope. Okay, let me go back in time. There, that was what we wanted there. And now this just needs to evaluate it and then ignore it. Hey, look at that. All right. That's a silly shortcut that I took a while ago and then forgot to fix it. All right, so let's go back and open up our test logs file. We have var a is equal to 1, a is equal to 3, print a, and a is now 3. Very cool. All right, so we have variable declaration and assignment. Of course, we've taken some shortcuts to get here based from the book. The main shortcut is Right now we've just stuck an identifier on the left side, but it could be an expression that evaluates to something that's assignable. So this would have to be assign expression, and in the lexer, no, in the parser, we'd have to change this to expression here, and an identifier would have to be a valid expression, which it is. And what else do we have to do? Eval now, ID, I guess ID is kind of, yeah, it's okay. We'll leave that there as ID. Let's see if that still works. Nope. What do we have here? Print ASD, okay. Print ASD and eval. The expression has typed string, but an expression was expected to type expression. Okay. So now we have to essentially turn our expressions into strings. Yeah, I'm gonna actually, yeah, we can try and solve this real quick. So when we actually are doing, let's start with variable declaration, I suppose. No, this is always going to be a string. That's fine. When we do assignment, this identifier is an expression that needs to be turned into a string. So we need to we essentially need to check to see if it turns into an identifier or a field. I think we're going to push this off to the future. So I'm going to change that back to identifier, and then the AST, I'm going to change that back to string. Okay. All right. So we have assignment and declaration working. Next time we're going to take a look at scope. In between then, I'm going to try and clean up the code a little bit and add some error handling. But we'll pick up with scope in the next video.